So here are the objectives of this lecture. In this lecture, we will explain the timing requirement of a real-time system, and we will also distinguish between what is hard real-time system and what is soft real-time system. We will also discuss different characteristics of a real-time system and further describe the scheduling mechanisms in these real-time systems, that how they are different from normal systems. So real-time systems are those systems which required to complete its work and deliver its services on time. You can also say that real-time systems are time-bounded systems. You are bound to meet the deadlines. And here you can see the examples of real-time system is a flight control system. You can see that there are thousands of flights on different airports of the world, and they share the same airspace. So every flight should meet its deadline and use the allotted time slot for its flight. If any flight missed, then it will be scheduled whenever the airfield is free for flight. Otherwise, it may be suspended till next day. All tasks in that system must execute on time. And you can see that if you don't meet the deadline in this system, it may cause a big destruction, a big damage inside the system. Similarly, the embedded system is a computing device that is part of a larger system like automobile and airplanes. And as you know, that the new plane that are drone planes are actually a type of embedded system. Similarly, safety critical systems are those real-time systems with catastrophic results in case of failure. And that's what I also told you earlier, that in case of any failure, in case of any fault, there may be a big damage which may cause many problems for the whole system. Here we will define, on this slide, we will discuss about the hard real-time system and soft real-time system. So in hard real-time system, the system guarantees that real-time tasks be completed within their required deadlines. So means the deadline which is predefined for those tasks, then definitely those system will meet the deadline. And in case of any failure to meet the deadlines, that will be very dangerous and very fatal for the whole system. And he has given the example of the last slide, that is the flight control system. So in flight control system, if any flight is missed, or if any plane delayed its flight, then it may cause a crash between or among different airplanes. Therefore, they will suspend that flight when the airfield is free, or when there is no slot, then it will be scheduled on the next day. Similarly, soft real-time systems are a soft real-time systems that provides priority of real-time tasks over non-real-time tasks. And look at this, these real-time systems, even if you don't meet the deadline, it's not that much dangerous or fatal as the hard real-time systems are. Like example is that late completion of job is undesirable but not fatal. You can see here that late completion may be undesirable, that you should meet the deadline. Similarly, system performance degrade as more and more jobs miss the deadline, like online databases. And you see that whenever you request certain queries and the system didn't respond on time, then there is a bunch of queries at the end because the system is unable to respond on the given time. Though it's not very fatal or dangerous for the system, but as you know that it increases a burden on the system at later stage when he is going to avoid or not responding to the system queries. The role of an operating system in real-time system is really very important. We can have a standalone applications as well as we can have a group applications as well. In standalone application, often no operating system is involved. And the example is microcontroller or embedded systems. You know about that we have even a ROM inside a computer, and there are certain instructions which are stored in ROM, and system fully obey all those instructions to do certain operations. Similarly, you also know about robots. In robots, they have special microcontroller and chip which have embedded instruction in them, and the robot work accordingly as per those instructions stored by the programmer. You know about there are different types of those ROM, like EPROM, erasable programmable ROM, or double EPROM, that is electronically erasable programmable ROM. So you can change the set of instruction, and similarly the work or the application of that hardware or software will be totally changed. Yeah, is there any question? Okay. Some real-time applications are huge and complex as well. There are certain applications which are huge and complex, and for example, you can have multi-threads as well. There are multiple threads at different level, and similarly, if you divide it into different systems and you divide it into different level. As we discussed earlier, that we have two types of threads. One is user level thread and another one is kernel level thread. And they have different types of relationship as well. Complicated synchronization requirement is also there, and similarly, the file system or network or windowing support as well. There are certain characteristics of these real-time systems, like as we discuss about drone. So drone is actually designed for attack, that you should save your resources, you should save the life of your pilot, and still you are able to attack on any place you want to. So that's why the real-time systems are single purpose, just like drones. They are small in size, and you can observe the difference between the size of a drone and normal jet. These are inexpensive when you produced them in a large number. So inexpensive if produced in mass in a big number. Similarly, they have the specific time requirement that is important, that you should complete the task in the given amount of time. So these are the four major characteristics of a real-time system that should be followed. Real-time operating system characteristics are further explained here on this slide, and the first one is scheduling, that how you schedule these tasks with one another. Similarly, what about the resource allocation? If we explain it here on the whiteboard, you can see that here, for example, we have these processes, that is P1 are programs, P2 and P3. And how we will schedule these, for example, its execution should be completed before 10:15, this one before 10:30, and this one before 10:05. So look at this. In this example, we will give highest priority to those programs or those processes which are closer to, this is closer, right? So here in this case, the process, the program P3 is closer. Therefore, we will assign CPU to process P3. Similarly, you can see the resource allocation as well. So resource allocation will be again dependent on the deadlines. Similarly, interrupt handling, for example, there is an interrupt for from a program which is close to complete, which deadline is almost over or near to complete, then it will get the resources as well as its interrupt will be addressed on priority. And similarly, some other issues like kernel size as well. That the kernel size may vary from system or operating system to operating systems. Scheduling in real-time operating system, more information about the task are known and number of tasks. Look at this, you know about many things that was not earlier given in other operating systems. So these informations are how many tasks will be there. So based on these tasks, you would be able to assign look at this, the number of tasks, and based on these number of tasks, you would be able to assign times, or you can say assign CPU time to different programs. CPU times to different programs. Similarly, the next one is resource requirement, what resources are required, and you can also mention here that number B is so number one is which resources like printer, like CPU, like scanner, like camera, like communication link, like memory, etc. And similarly, this is B2 and this one is B1. And similarly, the time for which the resource is required. Like for example, at what time you will need a camera, and you have to write 10:30 to 10:55. Similarly, at what time you will look at this, it's not reserved for the whole life of that program, but you have to specify the time as well. 11 to 11:30 you need the camera. And similarly, how much extra space you will require in memory, you can say from 12 o'clock to 3 o'clock, because I will do some extra calculation, and for that extra calculation to store my metadata are partially processed data, I will need the memory. I will need the memory. So moving back toward lecture to the third point, that is release time. So look at this, as I told you here on this slide, that what resources are required. You can see here what resources are required here and what will be the time. So this is actually the release time. You will occupy the resource and you will release the resource here. So look at this, once you share the release time, then it means the system can commit with any other programs that it can get the resource at 11:31 and very next minute. Once the release time is mentioned, then the system can give the next time slot to any other user. Similarly, next time is the execution time. Execution time is again that how long it will require, and similarly the deadline as well, that what is the deadline of this node, and it should complete its execution before this. Being a more deterministic system, it is better scheduling algorithm can be devised. So you can see that as you know about that, what will be the result. If you complete it on time, then it means the system will work properly. If you don't meet the deadline, then there is possibility of some destruction are some programs or some processes in of the system. Here are some scheduling algorithm in real-time operating system. The first one is clock-driven scheduling. The next one is clock means the time is involved. Then the weighted round robin scheduling algorithm, that is actually another form of round robin scheduling in which again the time is involved. And then the priority scheduling as well, that is a greedy list or event time, event driven approaches as well. So we will discuss them one by one. And here you can see the first one is the clock driven scheduling, where all parameter about jobs, release time, execution time, and the deadline is known in advance. So look at this, you have to give all these information of every process or every job or every program who want to go into the critical system. Then you should know about all these things. Schedule can be computed offline or at some regular time instances. You should also schedule these program to decide which one should move next for execution or for processing. And you can also do it offline, because you know about the requirement, the time requirement, the resources requirement, the execution time, and all those in advance. So that's why, because of those information, you can take these decisions. Similarly, minimal runtime overhead, you can change certain decisions at runtime as well. And most of the decisions are earlier taken. That's why there is less overhead in runtime. It is not suitable for many applications, especially for those applications who are dependent from some user, from some on some users or on some other programs, or they get some input from other programs as well. So in case of any delay in the execution or any other means mishap happen to other program, then definitely this program would not be able to meet the deadline. Next is the weighted round robin scheduling. In these jobs are scheduled in a FIFO manner, and FIFO is actually first in and first out. You can see we have different types of algorithm that are mostly used. That is FIFO, and FIFO stands for first in, similarly we have LIFO, last in, first in, first out, last in, first out, and last in, last out. So we have different types of algorithm that can be used for scheduling purposes as well. The time quantum is given to jobs in proportional to its weight as well. And look at this, you will give the time based on your weight, and your weight should be defined by your priority, by your deadline, by your memory requirement, and by dependency of some other jobs on you as well. Example is that you can use high speed switch network and quality of service guarantees. So these in a high speed network, you actually assign priorities to those packets, to those frames who are going to expire in the next few clock pulses. Or similarly, whose number of half or time limit is about to over. It is not suitable for precedence constrained jobs. For example, job A can run only after job B. And as I told you that there is some dependencies of job on each other. So it will not be a very good approach in that situation. No point in giving time quantum to job A before job B. So you cannot assign it if there is any dependency, as discussed in the last lecture, that if, for example, B is dependent on A, then it means that A should be executed first before B. You cannot execute B before A. The reason is B is taking some input from the A node. Another one is priority scheduling, where priority is assigned to certain processes based on different parameters. The processor never left idle when there are ready tasks. Processor will never go in waiting state or in idle state when, and they will provide the necessary processes or programs for execution. Processor allocated to processes according to some priority. Look at this, you have to assign these processes based on different priorities, and the priorities can be static or the priority can be dynamic. And if, for example, the priority is static, then it means the owner or the user will define it. Yeah, wrote the FIFO and LILO is actually, FIFO is used for first in and first out. For example, you do in stick, first in and first out. Let me explain it here.
I understand, but if it's the last in, last out,
Excuse me?
I mean, if it's the last in and last out, that's the same as the first in, first out, because you're basically doing the same thing, but you're just saying it in a different way.
Let me explain it over here on the sheet. So for example, if we have a queue like this, it is closed from here, and you are putting balls in it. So the first ball will come here, then 2, then 3, then 4, and then 5. So look at this, there, this side is closed. That's why this is last in and first out, right? Now, if you open this side, for example, one, 2, 3, 4, 5. So here, if you start, this is open, and you can, so first in and first out, right? And similarly over here, so here, fifth is the last, last in and last out.
Right, which means the first one you're going to take out is number 1. So the LILO, last in, last out, is going to behave exactly the same as the FIFO. So I was trying to understand what the difference was.
Yeah.
Thank you.
So it's almost the same. Is it clear?
Yes, thank you.
Thank you. So here the priorities can be static. At design time, the administrator or the owner or the user will decide this priority, or it can be dynamic, and they will change from time to time. And the example of static is that as your classes schedules are predefined, while in dynamic you can say that you can change your decisions of light, that once you take off, then maybe it's a kind of cloudy weather, it's raining, or there is some issue like snowfall, then you can take the decision to continue to fly, or you should return back to the starting point. So that is a kind of dynamic decision which may changes as per the existing situation you are facing over there in the system. Here you can see the priority inversion. Over here on y-axis we have priority, and on x-axis we have time, and you can see the task A started, then onward when the task A is completed, then the task B started, and then task C started over here at this point. But task B actually didn't complete its execution. That's why when task C completed its execution, then task B started over here. Here are the priority scheduling. You can see the first one is the earliest deadline first. The process with earliest deadline first will get high priority. And as we explained earlier as well, that you have some processes 1, 2, 3, and you will assign them priority based on EDF, earliest deadline. And in this example, as we discussed, 10:05 is the earliest deadline, then 10:15 and 10:30. So based on this algorithm, the process number 3 will get the resource. Similarly, next is about least slack time first, and the slack is actually relative deadline minus execution left. How much time? This is actually the remaining time. For example, we already have this program in execution. For example, there's another program that is P4, and we already have this program in execution. And you can see what is the remaining time. So for example, if it's 5 minutes and the remaining time of this program is 2 minutes, then definitely you will assign some priority to this one, because the time left for this program is less than that, and that's why the resources will be assigned to that one. The next one is rate monotonic scheduling, that is RMS, a priority assignment algorithm used in real-time operating system with a static priority scheduling class. And the task priority is inversely proportional to its period. As the period is longer, then the priority will go down. And this is almost just like we have SJF, that is shortest job first algorithm. Similarly, resource allocation, the issues with scheduling is applicable here. Resources can be allocated in, look at this, in weighted round robin as well. And similarly, it can also be assigned based on priority. So look at this, we have these flexibilities, we have these liberties to assign these resources based on the type of system we have. If it's a kind of hard real-time system, it will be very difficult for us to take any risk. While in case of soft real-time system, we can go for different options. Some resources are non-preemptible, as we discussed in last class as well, that they don't allow anyone to take the resource from them unless and until they complete their execution. The example is semaphores, which are protected variable that can facilitate and restrict access to shared resources. So it means they don't allow anyone to take their resource, to take their files, or to utilize their memory unless and until they don't complete their task. The priority inversion, if priority scheduling is used, you can also invert these priorities based on a certain mechanism whenever you are using this mechanism. Here is another system that is again system on chip. Earlier we have the concept of, if you remember, it was actually like we have computer first generations, in which we have vacuum tubes. Then computer second generations, we have transistors. In third generation, we have ICs. In fourth generations, we have microelectronics and nanoelectronics. So it means there are XLI and or you can say LSI. And over here, VLSI, XLSI. And this is large scale integration, and this is very large scale integration, and this is extremely or extra large scale integration. So same is the case that you have the embedded system, and in these embedded systems you have a set of instructions on a single chip. And now onward, you take this to the next step and bring a complete system on a chip. And now you have everything on a single chip. That include memory, that include processor, that include the communication link, that include the processing power, and that include any other hardware you actually want. And after that, the next advancement that is done over here is the network on chip. And now you have these chips. This is a single chip over here. So you have actually a network of chip on a single chip. And these all chips are connected with one another. So they are communicated with one another. And that's why you can say a network of chips on a chip. So here is the system on chip. Many real-time systems are designed using system on a chip strategy. where system on chip allow the CPU, the memory management unit, and attach peripheral ports like USB to be contained in single integrated circuit. And you can see over here, here's the USB port, system on chip, ROM, cache, DRAM, and similarly your CPU. And you can further see system on board as well, and system in package as well. So this is actually the new way, and you can also see here that this is a complete system that you actually put on a single system. This is a bus-oriented system where your CPU, your disk, your USB, your graphic adapters, and your memory are connected with one another. So all these devices will be connected on a single chip through certain buses. There are features of real-time kernels. Most real-time systems don't provide the feature found in standard desktop system. And the reason is that real-time systems are typically single purpose. As we also discussed earlier, that these real-time systems are single purpose system, and these systems often don't require interfacing with the user. As we discuss about the robot, that you have a set of instructions in that, and once the instruction is executed, then the system will do accordingly. If you want to change the functionality of that system, then you have to replace or you have to update that set of instruction in that system. There is no interface with which you can interact with that users, just like computer. Features found in desktop PCs require more substantial hardware as well, and that's why the hardware requirement will vary as the software requirement is different. As you are looking at this, that what kind of operating system they are using, either it is hard, either it is soft, or it is some other type of operating system. So they may vary from system to system. Similarly, real-time addressing mode where programs generate physical addresses as well. A drawback with real addressing mode is the absence of memory protection between processors. And the benefit is that the system is quite fast, that no time is spent on these address translation. If you go to the standalone system over here, you can see we have different types of addressing used for uh, programs. This is a CPU, and these are the CPU registers. Similarly, here is the cache memory, and we have a cache line. Here we have the RAM, the random access memory, and over here we also have some specified space for different program. And then onward we have the backing store, and in backing store you also have the virtual memory over here. And virtual memory is further divided or split into parts in which you can put your program. And further you have disks, and then onward on these disks you actually store your data. So what is the location of this over here? So the location address of that program like P1 will be different. Here the P1 address is different. Here the P1 address is different. Then P1 is moving here to the memory buffer register, MBR. We have different types of register here in the CPU, like we have MAR, memory address register, memory buffer register, IQ is the intelligence quotient, we have the accumulator, and we have ALU, arithmetic logic unit, and we have CU, that is control units. So we have these different types of registers in the system as well, and based on which you can decide that where the data is. And if you can see, at every location, the address is changed. So that's why he is actually sharing this here in this slide, that the location, the address of these nodes may be different. Look at this. Real addressing mode in the absence of memory. So here is the relocation register mode. Here a register R is set to memory location where program is loaded. And similarly, you can have the full virtual memory, which is created in the backing store. And in this instance, address translation takes place in page table and TLB. TLB is actually translation look aside buffer. Yeah, you can also see here the address translation over here. You have the logical address, right? And then you have the actual physical address, and then onward you have the relocation register address over here. You can identify these things over here. This is the CPU, which will provide the logical address. Then onward, the relocation register is here, that is R. Then onward, the page map table, which will help you to identify where actually this file lies. And you can see here that here the physical and logical addresses are almost same. But here in this case, you can see that physical location is equal to logical location plus relocation register entry. And these are these are the lines within the memory where you can locate where this program or where this process is, and you can locate it over here. Implementing real-time operating system must provide, number one is the preemptive and priority-based scheduling. And the preemptive is, that's why the preemptive approach is very important, because when there is preemptive approach, preemptive approach is helpful to address the needy and high priority jobs. So you can easily address, because in this approach, in preemptive approach, the program in execution allow you to take his resources whenever there is high priority task. So that's why it is important. This is task that you can see that in preemptive, they allow you to take the resources whenever you or the system need it. Look at this. Next is again the preemptive kernel as well. The kernel should do that as well. Latency must be minimized. You should minimize the delay, extra delay in the system, and there should be enough network support, which means that the network should be available to carry your traffic, to ensure that you can communicate anytime you want to your counterparts, your other nodes, to take certain decisions. Here you can see that minimizing latency over here in this diagram. What is event latency? Event latency is the amount of time from when an event occurs to when it is served. Over here I can explain you, for example, you can see where here we have a location over here. Here is a house, and there's a person and that location, and suddenly the house caught fire. He called the firefighter, and when the firefighter bus actually reached over there, then and they start the operation by putting the water on this fire, then this is the event happening time is 10 o'clock, and then when they reach here, that is 10:20. So this 20 minute is actually that delay. The 20 minute is this delay he is talking about here in this diagram. And you can further see here that here you can see the amount of time from when an event occur to when it is serviced. So actually when fire was burnt, that was event E that first occur at T naught. And the event latency in the real-time system respond to E is the T1. And this is the time when the firefighter reach the place and they start putting water on fire to control it. So this is the event latency. Another one is the interrupt latency. An interrupt latency is the period of time from when an interrupt arrives at the CPU to when it is served. For example, you can see here in this diagram, you have time in x-axis, and over here you can see this task is running. This task execution is in progress, and there is another program that interrupts over here. And look at this, he think either this interrupt is of high priority. If yes, then the context switching will happen, and then will be the interrupt service routine will be called over here. Let me explain it here a little bit to you. So here you can see that this is a CPU and program P1 execution is in process. This is time, right? At time number 6, program P2 actually interrupted, right? It interrupted over here, and in this state, the CPU will stop the operation and will start the comparison. Compare P1 is equal to P2, P1 is higher than P2, and P1 is less than P2. So for example, if the priority of P1 is less than P2, then automatically the control will be transferred over here and it will start execution over here. Over here, we will also do the context switching. The context switching is actually the process in which we store the current status of this program. Like we can see the execution of P1 was done till 6 point. And later on, next we will start execution from 6.1, then 6.2 and then onward. So here he has done and he completed his execution, for example, at 7 o'clock. And now the control will be returned here, and then onward the execution of this will start 6.1 and then it will reaches to 10. So this is actually the place that you do this comparison, and then onward context switching is done, and then give it to interrupt routine, interrupt controller to handle or to decide these. This is ISR, interrupt service routine, and then onward after that the CPU is assigned to that process. So look at it, this time, and over here the taking over of the complete control of this interrupt by interrupt service routine is actually called the interrupt latency time. And in this interrupt latency time, you actually take all those decisions. Over here, you can see you can decide the priorities, you can go for context switching, and then onward you can start the next process, the next process execution, or the way forward, you can say. Next is the dispatch latency. Dispatch latency is the amount of time required for the scheduler to stop one process and start another process. And this is actually, as I explained here, you stop here the process P1, you stop it here, and you start this P2, start this P2, right? So this is actually the time you consider it as a dispatch latency. You can see over here, here's an event, and the response to the event is also given over here. Response interval. The next one is the interrupt processing. You can see here, and the second line, and then onward the dispatch latency. So it is the amount of time. You can explain it over here. Over here, the amount of time that you stop P1 and decide to give it to P2, and then onward start execution process P2. So here actually this point you stop it and you actually jump from here to here. So this is the main theme of this process. Look at this. This is the dispatch latency, that you control one process and then give the control to the next process. Real-time CPU scheduling. Periodic process is required the CPU at specified interval. And over here, P is the duration of a period, that is the time. D is the deadline by when the process must service. And T is the processing time. T, how long it will process. So over here you can see you have different types of periods, like this P, and this P. And over here you can see in period 1, the time T is the execution time. He even didn't spend the complete period. But in second, you can also see have the same situation over here as well. And then in the third, so scheduler can assign priorities according to the deadline. So which one will complete first, then you can assign priorities based on this. So similarly, you can also save time as well. Scheduling of task when P2 has a higher priority. So look at this, when P2 has a higher priority, you give the control or the CPU resource to P2 first, and then onward the P2 completed the execution at 35, and from 36 you start execution of P1. As compared to last slide where it took 100 minutes to complete both execution of P1 and P2, you actually complete it in 55 minutes. That is almost 50% less than the last slide. Similarly, rate monotonic, mono means one. So rate monotonic scheduling means that you have to assign a single period or single time slot to each program. A priority is assigned based on the inverse of its period. As the period is higher, so it means the priority will be lower. As the period is lower, then it means the priority will be higher. You can see here is the inverse relationship between both these entities in rate monotonic as it is discussed here. So in rate monotonic, you can see here priority is directly proportional to period, and period is equal to time for execution, right? So if you have larger period, for example, you need 10 to 50 minutes, it means the priority will be less, 1 or 2. If you have lower period, just like 15, then it means your priority will be high and will also be increased here. You can see here, then it in rate monotonic, P1 completed the execution, started, and the period here was 20. The period here was 20 minutes, and then onward it is assigned for next 30 minutes to P2, and then after that the P1 slot started. And then P1 completed its execution, and then onward P2 completed its execution. In next slot after 100, the P1 again start, then P2, then P1, and then P2. So if you can see over here, this is the 100 is actually the point where they should complete the execution. But because of this scheduling mechanism, the rate monotonic scheduling, we actually complete this execution almost 23 minutes before. Similarly, the missed deadline with rate monotonic, you can see over here, P1 has 25 minutes, then P2 has 25 minutes, and then you give 25 minutes to P1, but meanwhile, you don't have enough time to complete P2. Complete P2, the P2 execution must be completed before 80, but you give more time to P1 because of the monotonic scheduling to P1, and that's why P2 missed the deadline. And in such situation, we didn't meet the deadline. That's excuse me. That's why we change it to the different priority that is actually, as we say, that how much time is remaining for this program. Or you can say the earliest deadline for scheduling can be used over here. Priorities are assigned according to deadlines. The earlier the deadline, the higher the priority would be. For example, if you have a deadline that is earlier, then you can also check it over here in this diagram. The later the deadline, the priority will be lower. You can see over here in this diagram, he assigned the CPU to P1, then onward to P2. And look at this, the P1 deadline was 50, but he assigned it earlier, and then the P2, and then P1. So look at this, the time for P1 to complete the first lot was 80, but he completed at 60 over here. And similarly, P2 over here, P1 completed 100, but he completed here at 85. And then onward over here, the P is 125 P1 and then P2. So the total time in which the P1 should complete its execution was 150, but though P1 completed its execution at 125. 125 it completed its execution. Then similarly P2 was supposed to complete its execution at 160, but it actually completed its execution at 145. So this is very important to mention that you should assign priority based on the time in which they will complete their execution. Proportional share of scheduling is also given here, where T shares are allocated among all processes in the system. An application receives N shares where N is less than T. For example, this is total time and N is some numbers or some share. If T is 100, then N should be 50, 60, 70, 80, 90, always less than T. This ensures that each application will receive N by T of the total processor time. So for example, if there are 4 processes, then they will get 25%. If there are 5, they will get 20%. If there are less, then they will get more time. Here is the POSIX pthread library, which is used in Windows. The pthread API provides function for managing real-time threads in operating system. It also allows a program to control multiple different flows of work that overlap in time as well. Sometimes there may be the overlapping between different programs, and you have to solve that overlapping problems and take the decisions. The pthread defined two scheduling classes for real-time threads, and that is actually the mechanism to resolve these issues. The first one is a schedule FIFO, where threads are scheduled using first come and first serve strategy with a FIFO queue, and there is no time slicing for thread of equal priority. No time slicing, remember, no time slicing, but only when the programs or the threads have equal priority. If they have different priority, then there will be a time slicing based on their execution. Similarly, another one is scheduling round robin, that is totally time based, similar to shed FIFO, except time slicing occur for threads of equal priority. And this is almost except time slicing occur for threads of equal priority, that you have to define the time, and you should define the period, as we discussed in last slide, that they have defined a period for P1 of 20 minutes or 20 seconds, and then to next P2, P3, and all of them completed their execution in the given time. Here is the VxWorks, which is a real-time operating system, and that was developed as proprietary by a WinDriver of Alameda, California, US. And you can see over here in this diagram that there are different types of libraries used by these operating systems. It also uses POSIX, the Java, the virtual memory, and similarly graphic library as well. And it also uses the microkernels, Win microkernels. for this purpose. So there may be many other real-time operating systems. It can be your homework you can submit in next class about what are other different real-time operating systems, and compare them with each other based on their library, based on their microkernel size, and based on the scheduling algorithm they are following. So this is your homework for today. And when microkernels provide support for the following processes and threads. Look at this: preemptive and non-preemptive round-robin scheduling. It also manages interrupt with bounded interrupt and dispatch latency times. It also shared memory and message passing inter-process communication, that is IPC, inter-process communication facilities as well. So this is the end of today's lecture. If you have any question, you can ask